All right, so here is a container. Okay. All right, let's get started. Here's a container at the front of the room, and it contains thousands of beads. I couldn't find one that actually had thousands, so just bear with me. Imagination, right? The goal is to estimate the mystery proportion of the beads that are red. Instead of simply giving a single value estimate, each group will use a sample to create an interval of possible values for the mystery proportion. The group with the narrowest interval that actually captures the true proportion wins a prize. So, we're obviously not going to do this because otherwise it would take forever because I don't trust y'all with samples anymore. So we're going to select a random sample of 20 beads from the jar. All right, so let's say that this obviously is not 20 beads, but again, it's okay. We're going to calculate the proportion of beads that are red. Let's say that the proportion is 0.35. Okay, so we take a random sample and we get 0.35. This is what we're going to call our point estimate for the true proportion of red beads. So what is the population for this scenario?
1.
Mm.
Oh, wait, no, the thousands of beads.
Okay, so all the beads in the containers, or the thousands of beads, all the beads in the container. Okay, and then you also just told me the sample, the 20 beads selected is the sample. We've been talking about parameter and statistic. Parameter goes with which one? Population or sample?
Population.
Okay. And then statistic goes with, okay, the best way I remember this is PP and SS, right? So parameter is going to be P, which is going to equal the true proportion of red beads. Red beads. The statistic is going to be P with a little party hat. So P hat is equal to 0.35. This is what we're going to call the point estimate. All right, so now we're going to choose a value to add and subtract from your point estimate. This value is called the margin of error. Have you heard of that before? Yeah, okay, cool. Plus minus, okay? So we're going to create an interval of values. Remember, the narrowest interval that actually captures the true proportion wins a prize. So what margin of error do we want to use? Okay. Say it again. So we want to add and subtract. So we're going to add and subtract. Ooh, not the right one. Add and subtract 0.1 maybe. And the reason why we want to choose this is because it's about 2 of more or less red beads. Okay. We're going to use our point estimate and chosen margin of error to create an interval. So 0.35 plus 0.1 would be what? Okay, so 0.35 plus 0.1 would be 0.45. And 0.35 minus 0.1 is going to give us 0.25. So our interval is going to be between 0.25 and 0.45. We love to see it. Why is it a 0.1? Because this thing is stripping. It's like spazzing out. Try this again. 5. There we go. And that's a parentheses. Yay. Thank you. So that gives us the closest interval. The smallest. It's like a narrow around it. Because look, 2 or more less red beads. That would give us that varying degree. Because we want it to be super small. Yes. Plus or minus. Okay, so this is what we call the confidence interval. The confidence interval. Yay. So that's where we took our point estimate, and we added and subtracted the margin of error. So point estimate plus or minus mo. Yes. But not that mo. Other mo. All right, so how confident are you that our interval covers the true proportion of red beads? So we took a sample and we got 0.35, right? And we're saying from 0.25 to 0.45 is where the true proportion lies. How confident are we? 90% confident that the interval from 0.25 to 0.45 captures the true proportion of beads in the container. Why do we have 90%?
Great question.
No, like this is the thing. It's.
What number did we use up here?
One, and I think, isn't that like the standard, like in this area, it's like 90%?
Okay. So that 90% confidence comes from that 100% minus that 10%. So we added and subtracted 10% from both sides. So we are 90% confident because of that interval that we used.
Double checking.
Go ahead.
Are we adding or subtracting 0.1 because it's 10%, like it's 10%, or are we adding or subtracting plus 0.1 because it's too small of a number?
Because it's that 10%.
So
We want it to be narrow
why do you write the answer to the question like that?
because it only gives us a little bit of a variation from our proportion.
I should write it.
Say again.
Because it asks like why do we use 0.1,
Mm-hmm.
and that was the answer. So that's why I'm out.
So from our sample of 20, if we said that the proportion is 0.35, how many red marbles did we have? 7. Okay. And we want that interval to be super small, right? If we would have used 5%, that would have been one difference, right? Okay. We're using 10% because we want to be able to be 90% confident, 90 and above. Yep. That's
more confident.
So could you really like that true proportion when we actually do the next sample? Is it going to be that 0.35? No, there's going to be some variability every time that we take a sample. We're trying to say in between this range, we know that the true proportion is going to be there. Yeah.
The one that was it's like 290 there. Like it's not like it was like a boat.
That's why we have that interval, right?
Like, mine, I was, like, said it could be like 90% of the time. The proportion that we get is going to be within 0.45 and 0.25.
We're getting to that. Yes. All right. So this is what we call interpreting the confidence interval. That's interpreting the confidence interval. Okay, so just like what Victoria was just saying, we are 90% confident that the interval from 0.25 to 0.45 captures the true proportion of the red beads. Okay, that's what you're going to say when you interpret a confidence interval. Now, one group claims that the true proportion of red beads is 0.4. Does your interval support or deny this claim? Support, right? Why? Okay, because 0.4 is in between 0.25, and 0.45. Yep.
Why is confidence on-
So whenever we are taking a sample, each sample is going to be different. We're trying to find the true proportion without having to count the thousands of marbles that are in the jar, because that would take you a really long time, right? Samples are supposed to help us with trying to interpret what's happening in that population, but being able to replicate it over and over again. There's going to be room for error whenever we take a sample from that population. Does that make sense? Okay, so that's why confidence intervals are important.
So, okay, so when you took your first sample and 0.35 was the amount of red beads you had, right?
Right.
And then you're adding and subtracting because this is like, okay, so like if you get any sample, there should be any sort
It
of.
should be falling between 0.25 and 0.45.
But like, what if that first sample that you did, you just happen to get one red,
Okay,
and there's so much more red in the finish red.
so then would that really be a good sample?
Yeah, but
And you have to use the the experiment to get a better idea.
but how would you know whether it's a good sample?
I mean, you just said, well, I've looked.
I said that like it's,
Right.
but then again, like I've never seen the jar.
Right.
That's why you have to repeat it. Like, when people get statistics in the real world, they don't only go for like one group. Or if they even do one group, it has to be in a certain
So
amount.
then what makes this draw a good draw?
Well, you will replicate it over and over again. We would each do it individually. But again, we are not going to go count 1,000 marbles. Like, we're not going to sit here and count them all out.
And then these questions are gonna like keep in mind, like, oh, we did this like thousands of times, because this is the test results.
So let's look at the next one. Let's say that another group got between 0.27 and 0.33 as their interval. So they did a sample and it was a little bit lower this time. So just like what you were talking about, David. And so we're going to try to find their point estimate, right? Okay. So remember, point estimate is going to be halfway between our interval. Okay. So point estimate. Stop. Point estimate is going to be halfway between 0.27 and 0.33. So 0.27 plus 0.33, and we're going to divide it by 2. The reason we're dividing by 2 is we're finding halfway between those 2 points. Okay, so that's going to give us 0.30. Okay, so again, for interval A to B, we would find the point estimate by taking A plus B and dividing by 2, right? It's the average. Go ahead. We're finding the point estimate. So we were given the interval, we're finding the point estimate. Point estimate is halfway between. Yes and no. It's the middle part. It's our point estimate. It's what we found in the sample. Like they sampled and they got 0.3 this time. What is their margin of error? 0.03. How did you get that? Okay. All right. Or another way you could have done this is you could have taken your 0.3 minus your 0.27 and dividing it by 2. That gives us 0.03. But just like what he said, you could take 0.33 and then subtract 0.03. All right, go ahead and flip the page. Okay, so for your quick notes, we talked about interpreting the confidence interval, interpreting the confidence level. So that's where we said if we take many samples and calculate a confidence interval for each about blank percent of them will capture true and then whatever your context is. So if we take many samples and calculate a confidence interval for each, about blank percent of them will capture the true, whatever your context is. So like last time we were talking about the red beads in the jar. And whenever they say interpret the confidence level, this is what you would use. So when we talk about part B on the check your understanding, that's the phrase you're going to use on part B. No, that's the confidence interval. Okay. And then the other thing that we talked about is the margin of error. So when your confidence level goes up, your margin of error also goes up. Okay, so when we did our proportion, we said 10%, right? We covered a wider interval. Oh, yeah. When your sample size goes up, your margin of error goes down. That means that you have a narrower interval. So the confidence interval is the numbers that we had from 0.25 to 0.45. Yeah. N is your sample size. Your confidence level is the percentage that we talked about. Yep.
How does the confidence level go up when the margin of error is good?
So your confidence level goes up because you're expanding your interval. Like if I say that your grade falls between 0 to 100, I'm 100% confident that your grade falls between 0 and 100, right? Yes?
But
That's a big range, right?
earlier,
Now, if I sit here and I go, you fall between 30 to 50, that may or may not be true. I'm not so confident anymore, right?
so earlier, when you got your 90% confidence level,
Mm-hmm.
did you subtract 100 by 10 or whatever
Mm-hmm.
and got the 90%?
Mm-hmm.
So if you get like, if you have like a margin of error like 0.3, why would it not be a confidence level of 0.7? Because are you not still doing 100 minus that 30?
Yes.
Right. So the confidence level just decreased over there. at least just from what you showed us earlier. When you got the margin, when you had the margin of error of 0.1, you got the confidence of 0.9 because you did 100 minus 10, that would be 9%.
Right.
So if I had a margin of error of 30, I would do 100 minus 30, and I get a confidence of 30.
Right.
So how do they both increase when it's not today?
I hear you. I gave you the wrong page. That's why. You're doing great. Welcome to Tuesday. You're okay. Don't erase anything. Don't erase anything because that's for the next one. Okay. Let's look at check your understanding and let's walk through these together. Okay. Ready? All right. I will clear this up. Ready? All right. On a random sample of 100 adults, we were asked if they pay for monthly subscriptions they do not use, such as gym memberships or music or video streaming apps. Many people say that these subscriptions, because they hope to use them more, or that it is hard to cancel the subscription. So a 95% confidence interval for the true proportion of adults who pay for the subscriptions they do not use is 0.352 to 0.5548. So we're going to interpret the confidence interval. Okay, so how are we going to say this? We're going to say that we are 95% confident that the interval from 0.352 to 0.548 captures the true proportion of all students, or I'm sorry, all adults who pay for subscriptions they don't use. Okay, so what we did here is we just said, here's our confidence interval. They gave it to us. Here's our interval. And we put it back in context. Okay, when they ask these questions, they're going to ask interpreting questions. All right, so now we're going to calculate the point estimate and the margin of error. So you're going to do the exact same thing that we did on number 7 on the previous page. Okay, so number 7 on the previous page. Go ahead and take a moment, go ahead and find the point estimate and then find the margin of error. Okay, there we go. Let me find it. Okay. All right, so for your point estimate, we're going to do 0.352 plus 0.548, 0.548, and we're going to divide it by 2. When we do that, we get 0.45. For our margin of error, we're going to take 0.548 and we're going to subtract 0.352 and divide it by 2. and that's going to give us 0.098. Again, the same thing that we did on number 7. So based on this survey, a reporter claims that a majority of adults continue to pay for monthly subscriptions they don't use. Use the confidence interval to evaluate this claim. Okay, so when we do this, we say because our confidence interval contains values that are above and below 0.5, we can't say that majority of adults pay for subscriptions they don't use. Okay, our interval falls between 0.352 and 0.548. That is neither the majority, like it's not more than, majority of that is not more than 0.5. We can't say for sure that the majority of the adults pay for subscriptions. So we don't have convincing evidence. We don't have convincing evidence. So because our interval contains values that are above and below 0.5, we can't say that the majority of adults pay for subscriptions they don't use. We do not have convincing evidence. Okay, so let's spend some more time with the 95% confidence interval. Let's talk about how do we find that, what does that actually mean, etc. Take out your laptop really quick because you need it for the next page. We're going to do this together. All right, so on your computer, you're going to set the population proportion to 0.5 and the confidence level to 80% and the sample size to 100. Okay, so again, proportion to 0.5, confidence level to 80%, and sample size to 100. Okay, you're going to hit sample. Okay, so what is your point estimate? Say again. Okay, so everybody's going to have a different one, right? Okay, so we're going to write on our paper whatever your point estimate is. Okay, so like mine was 0.48. Okay, what is the margin of error? So what is that plus minus that they added on to the end? Look at your paper or look at your laptop. And again, it's going to be a little different for every single person, right? What does the vertical green line represent? That green vertical line. The true population proportion. Because that's what we set P to be equal to. Right? Okay, so the green line is the true population proportion. So did this confidence interval capture the true proportion? So did your little confidence interval, did it capture 0.5 in the middle of it? If you added and subtracted those numbers, the margin of error, does 0.5 lie in the middle? Yes. Okay, so it should have. Okay, so what I want you to do is with your app, I want you to do this, run it 10 times. One, two, three, four, five, six, seven. No. 10. Okay, and you're gonna get something like this. What you want to do is figure out of the 10 samples that you take, how many of the intervals captured the true proportion. So for instance, on mine, 1, 2, 3, 4, 5, 6, 7. So mine would be 7 out of 10. Yours might be a little different. Okay, go ahead and take a moment. Go ahead and sketch that on your paper. Okay, so you are counting up how many times it hits that green line. The dot is the point estimate, and then the line is the margin of error on both sides. Okay, notice right here, it says percent hit, and I got 80 or 0.8. And that's because I got 8 out of the 10 that actually hit. So we're going to hit reset. Okay. And what we're going to do on this next one is we're going to take a total of 100 samples. We're going to sample 25 4 times. What is your percent hit? Yours is probably around 0.79. You might be 0.80. You might be 0.81. Okay. So my percent hit on that one was 0.79 or 79%. Okay. Now we're going to continue adding the samples until we get a sample size of, we get 5,000 samples. Okay. And the way you can tell is where it says total. So you're going to keep going until you get 5,000. Oh my Lord. A lot of clicking. Okay. So what is the percent hit? Yours is going to be around 80%. It's going to be somewhere in between 80 to 81. Okay. So we would have 0.811. Okay. So this is for number 5. It's going to be about 81.1%. Yours might be a little different. Okay. You took 5,000 samples that were completely on your own. So if we take many, many samples and calculate the confidence interval for each, about 80% are going to capture the true population proportion. So David, we were talking about on the last one, when we said 90%, that's if we ran it 5,000 times, 90% of them would fall in between there. Yeah. Okay. All right. So we're going to have about 80%. Okay, there we go. We're going to have about 80% fall in that range. 80% will capture the true population proportion. And we talked about this in the last one. We are interpreting that confidence level. Okay. Now, what happens to the intervals when we change the confidence level? So on your thing, I want you to change it from 80% to 95%. So 80% to 95%. So going back in here, if it'll load, I want you to change the confidence level from 80% to 95%. What happens to the intervals when the confidence level is increased? What happened to the interval as the confidence level increased? So here it was again. Confidence level is down here. Okay. The intervals get wider. Yeah, the intervals get wider. So coming back in here. When we click from 80 to 95%, the intervals get wider. And more of them capture 0.5. So we need wider intervals to be more confident. So that's where the confidence level goes up, the margin of error goes up, because they're more likely to hit that true proportion.
Is there a way to calculate confidence levels?
We're getting there. We're getting there. Baby steps. All right. So what happens to the intervals when we change the sample size? So now we're going to change the sample size. So go back to your page. And we're going to change the sample size to 20. Okay. We're going to keep it at 95% confidence. And we're going to take several samples. So sample, 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 sample. All right, so look at that. Versus a sample size of 250. And we sample, 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 sample. What do you notice? From if our sample size is 20 versus our sample size is 250, what do we have? There's more variability. What? Okay. Our intervals are much narrower though, right? For the sample size of 250. So as the sample size goes up, the variability, just like you said, goes down. Variability decreases. So as N increases, margin of error decreases. We get closer and closer to that interval. So when we increase that sample size, okay. Thank you. So we went from 20, we had a bigger margin of error. Why did we have a bigger margin of error on that? Do you remember what you said about the red beads? If you took a sample and you only got one out of that, that doesn't seem super reasonable, right? Bigger margin of error, smaller sample size. More sample, bigger sample size, smaller margin of error. So we got a smaller interval. We have a better depiction of what's going on in the jar.
It looks more like the actual population. Like,
You're looking at more of the marbles. Like if I'm looking at 250 versus 20, I know more about my population then.
Oh, okay.
Yeah? Okay.
I was thinking of sample size.
No. Okay. All right. Flip the page. I'll give you this one. Okay. Go ahead and take a moment. I want you to go ahead and try. I want you to try A, B, C, and D. Go ahead and try A, B, C, D. Okay, and then we're going to talk about it. All right, physical education teacher at a large high school wants to estimate the proportion of students at this school that can do a pull-up. Okay, now here's the deal. Like, it would take 5 million years for us to, like, take all 3,300 kids at the school and watch them sadly do a pull-up, right? I'm not wrong, it's fine. Okay, so he selects a random sample of 30 kids from those who are able after who are available after school for sports practices. He records whether or not each student in the sample can do a pull-up. He determines that he is 90% confident that the interval from 0.418 to 0.715 captures the true proportion of all the students that can do a pull-up. So he's like 40 to 72%, right? I guess pretty meh. Okay, so confidence interval. We are going to say that we are 90% confident that the interval from 0.418 to 0.715 captures the true proportion of all students that can do a pull-up. Now, keep in mind that he's just calling the people who are going to after school practices. The people who are probably going to after school practices probably are most likely to be able to do a pull-up. Just a thought. Like if they came in here, how many of y'all can do a pull-up? Okay. All right. Well, that was more than what I thought. Okay, cool. Cool. That middle school fitness test. Let's go. Yep, pacer and everything. And interpret the confidence level. So if we take many samples and calculate the confidence interval for each, about 90% would capture true proportion of all students students who can do a pull-up. Sorry, I got a little lazy at the end. Who can do a pull-up? Okay, so if we take many, many samples and calculate a confidence interval for each, about 90% would capture the true proportion of all the students. Okay, so that's exactly what we did with that little simulation. We took a sample, we ran all of those intervals, and notice how those lines were kind of all over the place. Okay, about 90% of those lines would fall in between these two things. Now, how would a 90% confidence interval from a sample size of 200 compare to the original 90% interval? So going from a sample size of 30 to now 200, what would happen? Increasing the sample size does what to the margin of error? Okay, so increasing the sample size decreases the margin of error, so it would be narrower. So for the next one, explain what would happen to the length of the interval if the confidence level were decreased to 80%. So it would be narrower. Yep.
On B and N, that's the student.
Because I said for the students who could do a pull-up, I couldn't fit it all in there. Yes, variability goes down as we increase that. All right, so part C and part D, both of them would be narrower. Yes. What? So, okay, it's plugged in. It does have the capability of Bluetooth, but like I'm hardwired in. There shouldn't be an issue. I just work here. I don't make the rules.
Don't worry, I'll take one back.
A Wacom pencil?
It's like a giant.
Whack students. All right, so it would be narrower on C, and it would also be narrower on D. We talked about how if you increase the sample size, we decrease the margin of error. We decrease MO. Okay. For D, if we decrease the confidence interval or confidence level, what would happen to the margin of error? If we decrease the confidence level, what happens to the margin of error? It would decrease, right? It would be a smaller one. So looking back at, just say skinny. Skinny. All right. So if we had this and then we went back down to 80, it went from being super wide to skinny. Skinny. Yes. So we would decrease the margin of error. Margin of error. Margin of error and confidence level, they go hand in hand. You increase it, margin of error goes up. You decrease it, margin of error goes down. Okay? All right, here's the problem. Describe one potential source of bias in this study. What kind of bias is that? Under coverage. Under coverage. Okay? Under coverage, because we talked about the after school kiddos are probs athletes. Okay? Everybody got it? You are done with notes, but in the back of your packet, okay, in the back of your packet, you have all of your little homework pages. Wait, I'm gonna sign off. Okay, so you can start to be on 8.1 and 8.2. Okay, 8.1 and 8.2. So you're not to take on Thursday. Yeah. Alice. Welcome. So here's the problem with last quarter. Majority of you were not doing your recommended assignments. And so what ended up happening was, you didn't do your recommended assignment, you failed the test, then all of a sudden you wanted to do a retake. You waited until the last second to do your recommended assignment, you didn't learn anything. Then you took a retake, and guess what? You got the exact same grade you did on the last one. So I'm trying to help you help me and not waste your time or mine. Like, that's what we're trying to do. If you spend more time on it, the better you're going to be at it. Okay, theoretically. So this, yes, will be for a grade. Yes, it will go into the grade book. It will be due Thursday. Just because you do it doesn't mean you get 100. Welcome to quarter two. All right, so with that being said, I need you to start doing your homework. Yes? Okay, so go ahead and get started on that. You can do 8.1 and 8.2. Okay? Excuse me. Thursday.